Okay, so I recently I've been observing several people who've come to me with some confusion on vectors and what is a vector quantity. So I'm going to do a little tutorial or a little video to kind of fill in the blank, so to speak. So first, let's answer the question: what is a vector? Okay, if I can write English today. What is a vector? So so a vector is it's a quantity. It is a mathematical quantity that has both what's called a magnitude and a direction. So the magnitude you're gonna have to bear with me here. I don't have a tablet, so I'm doing this all with mouse. So magnitude and direction. Let's make that in a different color. And if this is the first time you're watching me, it is I'd like to point out that I'm back in MS Paint because until I find something better to use, this is kind of the best thing that I have. So anyway, so we have a magnitude, which is it's often denoted as the absolute value of the vector. So let's say, for example, we have a vector f. Let me go down a size here. Let's say we have a vector f. So I come from a physics background. If you've seen my other video, that's it's very physicsy. So when I see f, I think of force. So we have a force. So we can write the magnitude as the absolute value of our vector value force, or our force vector. Like that, and then we can denote that that's equal to. That's typically just written as f without the without the little vector vector notation at the top. Okay, and the direction is a little bit more complicated because you can't just write the value like we have here. I mean, I can denote this as say if I have a force vector that points in to the north, I could say north. I could say it points in the north direction. I could also say that it points in a certain, if I have an XY coordinate system, with that being x and that being y, I can say that it points in the positive x direction, or in the negative x direction, over here. And I can do that using several different forms of notation with this this magnitude of f. And one way, and the common way to denote that, is to use what are called let me finish describing what a vector is before I get into unit vectors. So to answer the question, what is a vector? It is a magnitude quantity, or it's essentially a scalar quantity. So it's a constant that has a direction, which makes it not a constant anymore. So I think the best thing to do at this point is to just kind of move into an example of a vector. So let's go ahead and write down examples here. Let's just leave it at ex. get the show on the road here. Okay. So we have a coordinate system, as I said. Let me try to make that a little bit straighter. And that is a large line. So we have a coordinate system, and let's go back to the force. Okay, let's say I have a force vector on here, just because forces are cool. So let's say I have a force on here, and it's pointing, let's call this at an angle theta. This is the x-axis, and this is the y-axis. So one way I can write this, so this is our force vector. So one way I can write this is, oh, and there, I'm sorry folks, my secret has been revealed. This is not actually a black canvas. This is a white canvas painted black. But anyway, so you can see that, okay, so this is our force vector. So the way we would denote this is we have an x value here that spans the length. It's the length of this force vector along the x-axis, and then we can do the same thing for the y-axis. We have a distance here that it's the amount of this. In all honesty, I mean, it's the amount of this vector f that appears on the x-axis and the y-axis. And then the way that we write that, or can write that, is simply by writing the magnitude of f with a subscript y or a subscript x, just to denote that it's not the magnitude of f, or it's not the length of f. That's something to be said, is that this length here, the length of f is the length is equal to the absolute value of f, or the magnitude. So that's a very, very important distinction there that needs to be made. So yeah, we can write this f of x, or f sub x, and f sub y with the subscripts there, just to denote how much of this vector f lies along the x and y axis. And this is where we get to call these actually become not values of their own, but well, yeah, they become values of their own that we call components, namely vector components, or components of these vectors, and we can denote those by again calling those f of x and f of y. However, they themselves are not vector quantities. So actually, that's a misnomer there. They themselves are not vector quantities. However, they are pieces of a vector. So another way that we can write this is by saying that f, our vector f, now that we've broken these down into components, the component along the x-axis and the component along the y-axis, we can write these in what is called, actually, frankly, I don't know exactly what the name of it's called, but it is it's a standard vector notation that uses what is called a unit vector. And the unit vector, as I'll draw on here, is it's a vector that sits along the x or the y-axis, and I'll draw that in here. It's a vector that sits along the x or y-axis that has a magnitude, or a length of exactly 1. So this orange arrow here I'll draw, and that is the unit vector x. That can also be written, and you may have seen it before, as I hat, x hat or I hat, and that's just the unit vector. It means that it is it lies along the x-axis, and it has a unit length of 1, or it has a length of 1 which is called a unit length. And then you can also write this for the y-axis. This would be y hat, which can also be written as j hat. And that's just a way to show. This is just a way to denote a length along a specific one of the specific coordinates, either the x or the y, or if you have a three-dimensional system, then along the z. So so we can go ahead and denote this. This function f, and let me bad idea. Let me go ahead and erase this and draw it in a different color, because this is a different notation. So let's go ahead and we can call this. I already used orange for my angle. Let's use pink. Pink is a nice color. So we can write f, our vector f, as actually a sum of I hat and j hat. And the way we do that is we'll use this first term. This first term will represent how many I hats we have. So how many lengths of 1, or how many vector lengths of 1 do we have lying along the x-axis in f of x here? And the value of that is just going to be f of x, I of x. So for example, if we had, let's say, this f of x, or this, let's say this vector f, or this value f of x, it has a value of 3. Let's say that it sits at 3 on the x-axis. So then this component right here can be written as 3 I hat, because it is a total length of 3 from the origin. It is a total length of 3 from the origin along the x-axis, which is denoted by I hat, because I hat is equal to 1 along the x-axis. So that's denoted as 1 along the x-axis. So if you multiply this by 3, you're going to get 3 along the x-axis. Pretty, pretty self-evident there. So now we can add our y components to this, or our how many j hats we have, and the value for that is conveniently fy j hat. So if fy say is some number like 10, that would mean that we have 10 j hats, or 10 unit 1 or unit lengths along the y-axis. This could also be a decimal. Say that we have 3.5. This comes up the y-axis 3.5 j hats, and that would go into this slot here to denote how high, or what is our rise on this plot. So that's one way of writing vectors, one way of denoting vectors. Another common way to write this is, and I'll do this in another color. Let's do purple. So another way to write this is in a simplified vector notation, where we make use of not greater than or less than signs. It's like sideways carets. I don't know exactly what the symbol's called, but we'll make use of these, and we'll say, okay, so we have x hat, or f of x I hats, right? We have f of x I hats, or f of x number of ones pointing in the x direction. So we can write that in here, and I'll go ahead and write this in pink, just because I'm pulling it from that equation. So we'll have f of x I hats, and instead of writing the I hat in here, we're going to assume that because it's in the first location, much like if this were the point, 0, or I'm sorry, 3, 0. If this were the point 3, 0, the 3 denotes that it's 3 on the x-axis, and the 0 denotes that it's 0 on the y-axis. So it's just a coordinate pair. The x, y, and then if this were in 3 dimensions, you'd have a z point, or a z value for a single point. So this is very similar in notation, except instead of using the parentheses that you would typically use, you're using the square brackets, or not square brackets. That's a square bracket. These are the sideways, whatever. So you denote that, and then you put a comma, much like you were writing a single point, and then you'd put your f of y, because you're pulling that many j hats down here, and then you'll close it off with another bracket, and that's another way of writing your vector. So just to kind of generalize, I mean, this is very, like I said, it's very similar to writing a point. So let's say that let's do another example with more explicit results. Let's expand this a bit. I'm writing really big today. And let's go ahead and do another example, this time with actual numbers. So I'm going to draw another coordinate plane here, and it's easier if I use the line thing here. So I have another coordinate plane here. Oops. And I'm gonna let's use maroon. Well, let me see how. Oh yeah, that shows up pretty well. So let's go ahead and make it point really far out this way. Okay. Now I'm not going to guarantee that this is absolutely perfectly accurate. It probably isn't, and I'm not going to trust that it is. But it's very clearly longer, pointing more in the x direction than it is in the y direction. And that's what I want. So yeah, let's call this x and call this y. So okay, so we have this vector, and let's go ahead and give it a name. Let's see. Let's call this vector n, capital N. And actually, that isn't showing up very well. Not as much as I want it to. Okay, so let's call this vector n. That's a little better. So this is our vector n, and it's pointing in this or this direction at an angle that I'm going to call theta again. At an angle theta, and what excuse me. And what I can do is I'm just going to kind of map this straight down. Whoops. Map this straight down to the x-axis, like I did before, and I'm going to call this nx. Right? Or I was going to use explicit numbers for this. I'm sorry. So this is our vector n, and let's say it goes to a point. Let's make this a little darker. And let's say it goes to a point right here of 10, 3. So that means that if we're going to map this straight down like I just erased, that this value right here is going to be 10 on the x-axis, right? It has gone over 10 spaces, and if I'm going to map this over here onto the y-axis, this will be 3 spaces, right? It has gone up by a number 3 That's where this point is. So so now I can say that, okay, this is 10 units pointing in the pointing in the I hat direction. Pointing in the I hat direction. So that means that I can rewrite my my vector n. I can rewrite my vector n as 10 I hat. 10 I hat. Now that's not the whole story though, because we still have this 3 over here. And as I said just a couple minutes ago, this is a 3 pointing in the positive y hat direction, or j hat. I'm sorry, j hat direction, which means that we have gone a total 3 units of 1 in the positive y, or the positive j hat direction. So I'm going to add to this a total of 3 j hats. And this would be how I would write this vector. Either this, or I can use the alternate form that I showed down there, which is a little less common, I would say, or at least I've seen it a lot less this year than I did last year when we were going into this a little bit more in depth. It's more of a shorthand, and that would be 10 3 with the comma in here and then a close there. So those are 2 ways to rewrite this vector. Now, this isn't the only way to find these components. Or I should say, there is a way to find these components as opposed to looking at the point or being explicitly given them. And I'll go ahead and show you how to do that. So let's get another coordinate system on here, and it looks like we have some of our previous work filtering over here. So I'll just kind of block that off. And let's go ahead and draw another coordinate system, and I'm going to make this one a little bit bigger and mostly positive. And the reason I'm doing that is because we've been working in this this positive x, positive y space this whole time. So I'm gonna stay in this space just because it's a little bit more convenient to work with, because I don't have all these negatives floating around. However, if I were to work in one of these other spaces, like for example, if I had a vector that came back this direction, so it isn't all that positive. Well, you do the exact same thing that you did above, except instead of being a positive 10, or in this case a positive, instead of pointing this direction and being a positive vector and having a positive 3, it's going to have a negative 3. And the way you'd write that is either you can call this either negative 3 or positive 3 in the negative I direction, or the negative x direction, and that's where your negative would come from. Either way, you're going to get a negative. Just know that if you're putting the negative on the unit, or on the unit vector here, then this is no longer a 3, but a positive 3, right? But I find that kind of confusing, so I prefer to leave it on the standard coordinate system. This is in the I direction, but it's going negative 3 in the I direction, right? So that's what I personally prefer. That you can do it either way, as long as you know that this is in the negative direction. So the way you'd write that is, let's say let's call this n again. N is equal to and you'd have your -3 this time, right? And then let's call this 5, and then 5, because you're still pointing in the positive y direction. And then you can also rewrite this. So keeping the same numbers, you can rewrite this I plus j, and then just fill in your numbers here. -3, 5, same notation as above, just with a negative. So as I was saying before I started talking about negative vectors, there's a way to actually find your components as opposed to being explicitly given them. So I'm gonna kind of just make a nice 45-degree angle here, and the reason I can tell that is because all these pixels are nice and lined up, and it's very beautiful, and I like it. So a nice 45-degree angle vector here. Excuse me. And I'm just gonna tone it, desaturate the color here, and we can break this into vectors again by breaking this along the x and y axis, just like we did above. Okay. Oh, those are not vector quantities. So we broke this right along the x and y the x and y axis here, and now we have our f sub x. To keep with the kind of trend here, I'm going to call this vector f. That's pointing out here. And then this is our f sub y. So that is same trend here, same distance. We've just broken it up into components theoretically. Now we don't actually have any numbers here. Nobody's given us these numbers. We can just do this because we know that f of x, or f of y and f of x are how much. That's the distance of f on each axis. Now now I'm going to write in the angle here, which, as I said earlier, is 45 degrees, which will make this a little bit more convenient to be solving for. Just to know the angle. Now, if you don't know fy and f of x, you will know the angle. Sometimes they'll give you both. They have to give you at least one. Or at least typically they will. Either that, or you'll have some other kind of information to be able to derive this. Either that, or it'll be a theory problem and you won't have any numbers and you'll just have to use variables. But that's besides the point. So anyway, so you'll have this theta, this angle here, right? Well, the theta is only useful if we have a right triangle, right? So what I'm going to do is I'm going to take this vector here, this fy, and I'm actually going to move it over here to the other side, so that I can treat it almost very much like the leg of, and what do you know? Whoops. And what do you know? This looks almost incredibly like a right triangle, because it is. And I'm actually going to do something like that, and oh my gosh, it's a right triangle. Well, that's that now makes this theta a billion times more useful, and I will show you how that is so. So as I said earlier, this vector right here comes with both an angle, or a direction, which can be defined by an angle, and a magnitude, which is defined by the total length. So this length here is going to be the absolute value of this vector f. So that's going to this total length here is going to be our magnitude. And typically, if you're given a force, they'll say, oh, it's a force of 10 newtons, and not to be confused with n up here. This is the unit newtons. So 10 newtons of force, perhaps. That is going to be your magnitude of F, right? And if they say, 10 newtons at an angle of 30 degrees, which is an angle that's very often used, they're giving you both a magnitude and a direction here. So just keep that in mind. But let's say they give us the value of 10 newtons. So how do we find our x and y components here, or our f of x and our f of y? Well, we have a right triangle, and we know that. So let me write these in a different color. Sine. Yes, we're using trigonometry here. Sine of theta is equal to. And let's go ahead and I'm going to color code this a bit. So this is our hypotenuse, right? This is our opposite side. And let's see here. What's a good color? And this is our adjacent side, right? I don't really like the blue there. Doesn't really show up very well. Let's do a nice little purple. Oh, I've already used purple. Congratulations, you get to sit here and watch me pick colors. Okay, so let's use yellow. So this is our adjacent, or our adjacent side. So we know that sine of theta is equal to the opposite, or the length of the opposite side, which we know is Fy, and over the length of the hypotenuse. Well, like I said, we already know the length of the opposite side, that's Fy. So I'll go ahead and write that in here. And that's going to be over the length of the hypotenuse, which we already know is, that's our 10 newtons, our magnitude of F. So I'm just going to write, I'm going to write that actually in the solid blue, and I'm just going to write that as F. So just the magnitude of our vector, of our force vector. So this will be our sine theta. And now I can do the same thing for cosine. Cosine of theta is equal to, and now if you remember the wonderful phrase SOHCAHTOA, you'll know that cosine is opposite over hypotenuse. And as you've probably discerned, our adjacent is the same length as our f of x. In fact, they are equal. So I can say that this is actually, and why I left that line here, I don't know. Let me get rid of that real quick. So I'll go ahead and write that as our f of x over, and again, our hypotenuse is just going to be f, so I'll just write that as f. Now we have these nice, and I'm going to expand this a little bit more. So now we have our nice little equations here. Let me get back to where I was. These nice little equations here of sine and cosine. And what I can do is I can, I'm still in black here. I can take these f's and I can multiply them back over to this other side to to isolate my my f of x and my f of y. So I'll go ahead and do that. So I multiply them back over, and I'm going to get f cosine of theta is equal to f of x, or f sub x. And then I will get a the sine term, f sine of theta is equal to f of y. And that's going to be the force along the x and y axes. So this is a very important relationship to know here and understand. So now to be able to use these, and now this is where if you're just here to learn about vectors, this is kind of where the vectors end. I think I've pretty much said as much as I can, at least at an introductory level, about vectors. But now I'm getting into the more physics aspect of this. If you want to use these, you're going to have to use some equations. So, for example, common ones are the kinematic equations, or in the case of forces, I mean, you have force equals. Well, let's do that, because we have a force. We have Newton's equation, Newton's law. F equals ma. Now in this equation, what they don't show you is both f and a are vector quantities. It's not a sin to leave the vectors off, but it's technically incorrect. Both of those are vector quantities, unless of course you are talking just about the magnitude, which is also true. But this shows you a little bit more about it, because it says that, hey, this acceleration is going to point in the exact same direction as this force. So if you were pushing something straight up, it's going to accelerate straight up. Surprise, surprise, right? So okay, pulling these terms from over here, and sorry I just touched my mic. Pulling these terms from over here, you're going to have f of x and f of y. Now the reason, and let's say we're looking for an acceleration here. So if you want something a little bit more thorough, with an example problem of this, I have another video that does a two-string hanging box, where I have two strings and then a box hanging from them. Two strings at different angles. This is a really bad picture, but two strings, then I have a box of mass m hanging from it, and I go through and analyze the different forces acting on those acting on the box. So to use these, the equation f equals ma, what they indicate is, it's a vector equation. It says that, if you're pushing something in one direction, it's going to accelerate in that direction. Mass is a scalar quantity, of course. Kilograms doesn't exactly have a direction. So yeah, it's a direct correlation between the force and the acceleration. So for example, if you had a box and you were pushing on it with a force in, say, like I don't know, the upwards theta direction, or to keep consistent, let's write this in orange. In the theta direction above the horizontal, and then this would be your f vector. So the only way you would be able to use this is to split your equation into f and x, to determine the acceleration in the vertical and the horizontal direction. You could plug in f of x. So we could say 10 newtons, 10 newtons, or could we say this? Yeah, 10 newtons equals your mass times whatever acceleration it has. So 10 newtons right now is in the vertical theta direction, and your acceleration is going to be in the same direction. So so a little proof of this, and this is just a general thing. So the way you can write f is going back up here to the hypotenuse argument, the trigonometry argument, we can use Pythagorean's theorem here. We can say the hypotenuse, which has a magnitude of f squared, is equal to the magnitude of fy squared plus f of x squared. So so what we want to do, or what we can see here is we can rewrite the magnitude of f as a sum of these squares. So we can write so we could rewrite f equals ma as fy squared plus f of x squared equals m times, and then this is where your a is also split into components, because a is a vector quantity, and all you have to do is come back up here and replace these f's with a's, and you have your formula for a as well. So that's going to be times a of x squared plus a of y squared. So yeah, and then you can see that this is certainly a an unscripted video, because I don't know where I'm going with this exactly. But you can see that this relationship can be helpful, but only if you have each of these values known. So sometimes you'll have your vertical acceleration and your your vertical acceleration, which is your AY, and your horizontal acceleration, which is your AX. But you'll only know F. You won't necessarily know Fy and F of X, or one or the other. I'm sorry, not either. So you can solve. Let's say we don't know either of these. That was the correct use of that word there. So we can say, f squared. So obviously, pulling from this right here, if you square both sides of this, you're going to get f times cosine squared theta plus sine squared theta. And I'm sorry, this is going to be an f squared. So you're going to get this, but if you know the trig identity, you'll know that this is equal to 1, which brings us back to this. So this is not, the most explicitly useful equation, and oftentimes it's much easier to look at this in component form. So to look at forces in motion as components, and I'm going to expand my screen here a little bit because this video is taking a little bit longer than I thought it would, because I seem to ramble quite a bit. But anyway, so we can actually break this down if we have a coordinate system here, and we have a force. Whoops, that's not what I wanted to do. And we have a force pointing this direction. Pointing in this direction. We can actually, it would be in our favor to break this up into components, like we just did, and look at this as f of x and f of y. Because we can now put this into our equation, or not our equation, Newton's equation of F equals ma. And I'm writing this without the vector notation because we're going to be using our components, which are non-vector quantities. So so I'll be plugging those into this equation, now we can plug those into this equation. So let's start with f of x. So we'll get f of x, or f sub x, I'm sorry. F sub x is equal to a mass times our acceleration in the x direction. So, ooh, that's Christmas colors right there. So what you can see here is, okay, now we have two equations, or I can write the second equation. We'll have f of y equals some quantity m a y now. And now we have two equations with, if we're given that our acceleration is 0, both of these terms are 0, because if you have something that's not moving, it's not moving in both the x and the y direction, so it's sitting at wherever it is, and it's not moving. So both of these will be 0. And if we're given a force, well, we already know what these are. We can set that equal to F cosine theta and F sine theta. And all of a sudden, this equation down here that isn't exactly explicitly useful becomes a lot more useful when we split it into two separate equations. Because we're probably given this and this, and we're probably asked to find an acceleration or a mass. Or if we're given ma and we're given f, we're asked to find an angle. Or any of these things. I mean, we're given several of these, and then we're looking for some of the other ones. So that's what we can break that down into that, and then we can solve for whatever we need. Let's say we're looking for the acceleration in the y direction. We're given the acceleration in the x and theta. Well, we can solve for f over here. Solve for f here, and then plug f into here because we were not given f, and we'll get ma over sine theta, because we'll divide that over here. Actually, let me just write that out. We'll get ma x over cosine theta is equal to f. And now we can plug that in here and then solve for our unknown, or the unknown that we're looking for. Technically in this, we were not given f. If you didn't follow that, I mean, you can rewatch it. I'm assuming that ax and theta and m are all given without actually giving any values. So that's pretty much it. I mean, I have a much more thorough video that goes through the different forces and how to do that, and that one's a little bit more well thought out. If you have any questions, leave them in the comments. Because this video or this channel's new and I'm still I'm still kind of in school. Classes are still going on. I don't have tons of time, but I'll check them every once in a while, and I'll try to reply as best as I can. Again, if there are any errors in this video, especially with this stuff down here, just because I haven't exactly done tons of exploration in that area of the mathematics behind it, let me know. I'll correct my videos. If anything's horribly wrong, I'll go ahead and take my video down and make a new one. I'm here to learn. I'm here to teach. I'm here to help spread the knowledge as best as I can. And this is one of the best ways that I can think to do it. So thanks for watching, and I guess have a nice day.